7, which is just kind of fun. It's about a turtle named Goliath. So, number 7, yes. Thanks. Appreciate it. I had a black shirt on yesterday, so I thought I would color it up a little bit today. Alright, number 7, Goliath, a giant Galapagos tortoise living in Florida. Is he still living in Florida? I'm not sure. But he has a mass, or he had a mass, of 360 kilograms. Okay? Big tortoise. Yeah, tortoises can live a long time. That's true. I'm not sure if he's dead or not. I mean, like, think about Crush when Finding Nemo. He's like 150. So, I heard he's got a movie from that. I don't know. Oh God. You think it's a good whole movie about Crush? What? Not really.
Younger Crush?
Yeah, it's like a prequel.
100 Heroes Crush?
Yeah, it's like 100. Yeah, it's like when he was 100. But he's wild and crazy back in his life, you know, like back in his 90s. All right. So suppose he walks along a board that is hanging over a swimming pool. Why? 360 kilogram tortoise. Why not? The board has a mass of 600 kilograms, which is a pretty big board. And it's 15 meters long, but only 5 meters of it hangs over the pool. How far out from the edge can Goliath walk before the board begins to rotate and he falls in? Luckily, we have a very, very helpful picture. Yes, through the sun. The sun is really key to this picture. I mean, it is Florida after all. So. All right. So there's the. What do you think of my turtle? So it's the best I can do, like on paints or something. All right. So let's take a look at this turtle and this board. Okay. Let's talk about forces. What's the first force that we can put on this drawing? Okay, let's put the turtle, right? And we'll make, even though he's green in this picture, we'll make Goliath blue. Alright. So there's, alright. There's that, okay? Then, what other force we got in this picture? Okay, we have force of gravity acting on the board. Where does that force act? Where does gravity act on things? Down, definitely, okay? Where along the board is it going to act? Gravity acts right in the middle of that object. Okay? Does that make sense? It's a concept that we call center of mass, that the effects of gravity, both translationally and rotationally, can be assumed to occur at the center of mass. Just say again. That could be the case. The center of mass doesn't always have to be right in the middle of something. Okay? That in the case of a meter stick that's nice and uniformly distributed, yeah, it is. Okay? But something like this, right? Especially if I take this one, slide it over this way, the center of mass of this object isn't right in the middle anymore. Okay? So we have to look about where that is, and that, you know, that's for another day, which we probably won't get to. But anyway, because this board is nice and evenly distributed, we'll assume that the center of mass to be right in the middle. So gravity's effect on the board itself acts right in the middle of the board, regardless of the fact that some of it is hanging over the edge. Okay? We're okay with that idea? Now, the reason why this problem becomes a little bit tricky is because where's the pivot point in this problem? Is it the middle of the board anymore? No. Now the pivot point is like right there, right? This is, I can still have to move the whole picture. So the pivot point is right there. on the board itself acting at the pivot points? No. So do we have to consider the torque that gravity causes on this object? Yes, we do. Okay. So, regardless though, we want to find out that point that Goliath can walk to right before he would fall in. So the step before Goliath falls in, what will be true about the torque acting on that object? Okay? Right before Goliath's last step, not of his life, but of his trip along the board before he falls in, the net torque has to be equal to 0. Could have been his life, I suppose. If it was, 149 and 355 days, or 365 days, well, whatever.
Okay, let's
Yeah, anyway. So, two torques, right? Torque of Goliath plus torque of the board itself has to equal 0. Okay. Does that make sense? Are we okay with that idea? So, this problem comes same just as the last problem we did, right? Force of Goliath plus distance of Goliath times sine theta plus force of the board, distance of the board, sine theta has to equal 0. All right, so what are some things we have to do before we start plugging numbers into this formula? Pre-calculate the forces. That's one thing we could do first. Okay, so go ahead and do that. What else? What about our directions? One's positive, one's negative, right? Just to stay consistent with what we did before, why don't we call Goliath negative because he's counterclockwise? And then what about D in this formula? What did we say that D was? We want to know D for Goliath, right? That's kind of what we're solving for. What about D of the board? What did we say that D was? What's our definition of D? Distance from the center of rotation, right? It told us in the problem that the board, I believe, is 15 meters long, yes? Okay. The pivot point is here, and it said that the pivot point is where 5 meters is hanging off the edge. Okay? And I told you, where does gravity act on a board, or a uniformly distributed object? Right in the middle, right? So, what does D have to be for the board? 2.5. Everyone see where I got the 2.5 from? If we're still following along. That was good. That was a good fix. Alright, so let's plug those numbers in. Let's solve for D of Goliath. Do we have to worry about sine theta in this problem? Theta is just going to be what? Well, theta is actually going to be 90, but sine theta is going to be 1.
Tuesday and Wednesday.
Right. And the board is taking your call as a gravity is 7.5 meters to get that. Yeah, gravity's always the anti speed. All right, how's that? Okay with 4.2?